The next problem we're going to look at is example 3, which discusses on what happens when we lose a solution. In example 3, we want to solve the separable differential equation dy dx equals y squared minus 4. Before we go ahead and solve this, let me just kind of remind you something from algebra. If we had, let's say, like the quadratic equation, x squared equals to x, there's many ways to solve this, but one of the ways that we typically don't do it is we would not start by dividing both sides by x. If we did, we would get a solution. On the left hand side, x squared divided by x simplifies to x, and x divided by x would give us 1. So we do get a solution. We get the solution x equals to 1, but this was a quadratic equation, and we know that this quadratic equation should have two solutions. To find them, we could bring both terms to one side. We would then factor and then set each factor equal to 0. And what we see is that we were missing when we divided by x. When x is 0, we had division by 0, and so we actually lost the solution. This quadratic equation should have two solutions, x equals to 0 and x equals to 1. Something very similar can happen when we try to solve separable differential equations. Let's take a look at the one in example 3. What we can do is we can begin, let's go ahead and let's say multiply both sides by dx to start. So we want to get everything with x on one side, everything with y on the other side. Here the dx's cancel, so we get dy equals y squared minus 4 dx. We can now divide both sides by y squared minus 4. And we would have the following. We have dy over y squared minus 4 is equal to dx. So our differential equation was separable, and we're now going to go ahead and integrate both sides to solve. We'll do the right hand side first because it's easiest. The antiderivative of 1 with respect to x is going to be x, and then we'll put the constant of integration on that side. So the right hand side is going to be y equals x plus c, and now we just need to find the antiderivative of, and I'm going to write it as 1 divided by y squared minus 4 dy. This is a good review from something that you have seen in calculus too, but in order to integrate this function, what we're going to use is partial fractions. It's true that if you have a polynomial, here we have a polynomial in the y variable, that every polynomial with integer coefficients can be factored into a collection of irreducible linear factors or irreducible quadratic factors. Here, so we would start by going ahead and factoring our denominator. So we have 1 divided by the difference of squares, so we can write it as y minus 2 times y plus 2. So the irreducible linear factors we get are y minus 2 and y plus 2. This is a linear polynomial, so we could have a constant in the numerator. Likewise here, constant in that numerator. To solve this, what we're going to do is we're going to clear fractions by multiplying both sides of this expression by y. Whoops. Multiply both sides by the common denominator, y minus 2, y plus 2, y minus 2, y plus 2. On the left hand side we get 1 equals, on the right hand side after we distribute you should get a times y plus 2 plus b times y minus 2. And at this point in time, to proceed to solve this, you could do one of two things. Because we have just a bunch of linear factors, it makes it easy just to pick some values for y to solve for a and b, or you could expand it. Think of the left-hand side as a polynomial, think of the right-hand side as a polynomial, and if you think of this as equality of two polynomials, then what you would do would be to equate the coefficients. That would give you a system of equations, and that system of equations would produce the values for a and b. I'm going to use the simpler method in this case, and that's just going to be picking some values for y. For example, if we let y be equal to 2, then plugging 2 into this equation would give us y equals a times, let's skip to the chase a little bit, 2 plus 2 is 4. That would give us b times 0, which is 0. So we get 4a equals 1. A would be equal to 1/4. To find the value for b, let y be equal to negative 2. And then we would get 1 equals a times 0 plus b times negative 4. And that will produce the value b equals negative 1/4. So what we've shown is the following. Our original integrand, this 1 over y squared minus 4, we can rewrite it as a over y minus 2. Here I'll just bring the coefficient out in front, which is the same thing as 1/4 times y minus 2. And then we have this plus b over y plus 2, where b is negative 1/4, so it's going to be negative 1/4 y plus 2. So we're able to rewrite this. This is now going to be the integral of 1/4 1 over y minus 2 minus 1/4 the ln. So it's not, going to have myself, times 1/4 1 over y plus 2 dy. And now we can use logarithmic integration to get these answers. So this is going to be equal to, the antiderivative is going to be equal to, we have 1/4. This will be the ln, the absolute value of y minus 2, minus 1/4, the natural log, the absolute value of y plus 2. And that's what we have on the left-hand side of our differential equation here. So it's, and actually before we even plug that in, let's simplify this quite a bit. So this is going to be equal to, we could bring the exponent on to the inside using properties of logs. This would be to the 1/4 power, minus this will be the ln of y plus 2 in absolute value to the 1/4 power. We have the subtraction of two logs, that's the log of the quotient. This is the ln of the absolute value of y minus 2 to the 1/4 divided by y plus 2 to the 1/4. And then essentially, because they're both to the 1/4 power, we can write it as the entire fraction to the 1/4 power. So the solution to our differential equation is the following. It's the ln of the absolute value of y minus 2 divided by y plus 2 raised to the 1/4 power is equal to x plus c. And this is an equation where we can actually explicitly solve this for y. To get rid of the natural log, we would want to take and raise both sides as a power of e. The e and the ln would then cancel. And actually probably even before that. Yeah, let's do that. So let's bring the 1/4 out in front, sorry. There's no right or wrong way to do this, just kind of an easier way. We'll bring the 1/4 out in front first. That gives us the 1/4, the ln of y minus 2 over y plus 2 is equal to x plus c. If we multiply both sides by 4, that'll clear off that coefficient. So we get the following. The ln of the absolute value of y minus 2 over y plus 2 equals, when I distribute this through, we've seen this a bunch of times now, but we have our 4x, and then 4 times a constant. I'm just going to write it as yet another constant. Okay. Now let's go ahead and take both sides to the e power. So we're using e as the exponent for these. The e and the ln cancel, so we get the absolute value of y minus 2 over y plus 2 equals e to the 4x plus c. We can continue to rewrite this a little bit more. For instance, if you look at e to the 4x plus c, that's the same thing as e to the 4x times e to the c, where this is yet again just a constant. E is a constant. You raise a constant to a constant, you get a constant. So I can kind of rewrite that right hand side as c e to the 4x. So the absolute value of 1 minus 2 divided by y plus 2 in absolute value is equal to just some constant times e to the 4x. We know that the absolute value, so the absolute value of the thing on the inside, could be either equal to the positive or the negative of the thing on the outside. So I'm going to remove absolute value bars by writing y minus 2 over y plus 2 equals plus or minus c e to the 4x. And again, this is just thinking of it as a constant, either positive 1 or negative 1 times some constant. That's still going to be a constant. So I'm just going to, again, just call it c. It's just some constant, whatever it may be. And now we're ready. Let's see if we can go ahead and solve this for y. We're going to clear fractions, multiply both sides by y plus 2. We would get y minus 2 equals, on the right hand side, let's distribute. We're going to have y times c e to the 4x plus this is going to be 2c e to the 4x, and you can probably guess what's going to happen here. Some constant times that we're just going to call some constant. So we have y minus 2 equals y c e to the 4x plus c e to the 4x. We would like to bring all of our y terms to one side and all of our non-y terms to the other side. So let's subtract y c e to the 4x from both sides. And let's also simultaneously add 2 to both sides. So what we're going to have, here's my equal sign. These cancel. We have y minus y c e to the 4x equals, here these would cancel. We have 2 plus 2 plus c e to the 4x. And now we're going to go ahead and factor out the y on the left hand side. That'll leave us with a 1 minus c e to the 4x is equal to 2 plus c e to the 4x. And then we can kind of go ahead and divide both sides by this. And so what we get is the following. We have y equals 2 plus c e to the 4x divided by 1 minus c e to the 4x. So if we take a look at our solution, here's what we have. Our solution is y equals 2 plus 2 c e to the 4x divided by 1 minus c e to the 4x. And again, we solved it out. We have y minus 2 equals y c e to the 4x plus 2c e to the 4x. We got all of the y terms to one side, all of the non-y terms to the other side. So we added 2 to both sides. We subtracted the y c e to the 4x to both sides. That got all of our y terms on one side. All of our non-y terms are on the other side. And then to get the y by itself, what we're going to do is we're then going to go ahead, we're going to pull all the y out, factor it out, and then you can divide by this factors to both sides. So the solution to this differential equation is y equals 2 plus 2 c e to the 4x divided by 1 minus c e to the 4x. And depending upon the different values we choose for c, for our constant, we would get a different solution. For example, it's worth noting that if c were to be equal to 0, then this would reduce to y equals 2 divided by 1, which is 2, which is a constant solution. Okay? And if you kind of go back a little bit, this is what we refer to as kind of like our critical points. This would have been, if you remember, this is an autonomous differential equation because it only involves the y variable here. So we could talk about what the constant solutions would be. The constant solutions to this differential equation would be the ones where y squared minus 4 equal to 0, which would give us two solutions, y equals plus or minus 2. We see that the particular solution, I shouldn't say particular, but the solution y equals to 2 can be obtained from this form by choosing the constant value c equals to 0. However, it is not possible to get the equilibrium solution y equals to negative 2 as a result of taking any value of c. As a result of that, we refer to this one is what's referred to as a singular solution. So the reason why it's a singular is because it doesn't quite fit into this family of other solutions that we have, right? Y equals to 2, yes, it's a constant solution. We would have seen that by, analyzing it as an autonomous ODE. It makes that right-hand side function of y equal to 0. But this one here will not come out, no matter what value of c you pick. You would never pick up this constant, y equals to negative 2. And the reason why that solution was lost is, if you remember very back in the beginning, how did we solve this thing? Well, we started by separating the y and the x variable, and that required us to divide by y squared minus 4. Again, the caveat and the thing you got to be careful with is if you divide by a variable, it's possible that you could lose solutions, and in this case that would have been the fact.